Commercial airliners stay locked below 43,000 feet, even though we've had the technology to fly much higher for decades. The Concorde routinely cruised at 60,000 feet, and military spy planes like the SR-71 operated above 80,000 feet, but your typical Boeing or Airbus maxes out around 41,000 to 43,100 feet. Physics, biology, and economics all conspire to keep passenger jets trapped in this surprisingly narrow band of altitude. The air itself creates the most immediate problem. By the time you reach 40,000 feet, the atmosphere has thinned to about 1/4 of sea level density, and the temperature outside hovers around -56 degrees Celsius or -70 Fahrenheit. Jet engines are essentially very sophisticated air-breathing machines that need to ingest massive amounts of oxygen to burn fuel and produce thrust. When the air density drops by 75%, the amount of thrust those engines can produce drops roughly in proportion, and that's a problem. Even the most advanced high-bypass turbofan engines struggle to maintain both cruising speed and the minimum climb rate of around 300 feet per minute that defines an aircraft's service ceiling. Push higher, and the engines simply can't generate enough power to keep the plane in the air efficiently, which means you've hit a hard limit. Thin air creates another problem with lift. Wings generate lift based on a simple equation where air density times velocity squared gives you the upward force, and in thinner air, the aircraft has two choices: fly faster or increase its angle of attack. Both of those choices push the plane toward what pilots call coffin corner, and that's where things get genuinely dangerous. As you climb higher, two speed limits start closing in on each other like a vice. Stall speed sits on one side as the minimum speed needed to generate enough lift, and in thinner air this speed increases because the wings have to work harder. The critical Mach number sits on the other side as the maximum speed before airflow over the wing goes supersonic and creates shock waves that destroy lift and pitch control. For most commercial jets, this happens around Mach 0.75 to 0.82, which doesn't leave much room to maneuver. At 51,000 feet, these two limits are separated by only about Mach 0.2, which means the margin between flying too slowly and stalling versus flying too fast and losing control shrinks to almost nothing. A bit of turbulence, a steep turn that increases the effective weight of the aircraft, or even a small gust of wind can push you across either limit, and the results are catastrophic. China Airlines Flight 006 gives us the most famous example of coffin corner going wrong. On February 19th in 1985, this Boeing 747 SP was cruising at 41,000 feet, about 300 nautical miles northwest of San Francisco, when the number 4 engine malfunctioned. The autopilot tried to maintain altitude while airspeed bled off. The aircraft rolled and entered an uncontrolled descent, then plunged 30,000 feet in about 2.5 minutes before the crew managed to recover at 9,500 feet. The plane experienced forces of about 5 Gs. The wings were permanently bent, parts of the horizontal stabilizer were torn off, and 2 passengers were seriously injured. That's what happens when you lose control at high altitude because you have a lot of sky to fall through. Your body presents what's arguably the most important constraint. Human beings need oxygen, and at high altitudes, even if you're breathing as hard as you can, there simply aren't enough oxygen molecules in each lungful of air to keep your brain functioning. The FAA has a measurement called time of useful consciousness, which tells you how long you have between losing oxygen and losing the ability to do anything about it, and the numbers are terrifying. At 18,000 feet, you've got 20 to 30 minutes, which isn't great but is manageable. At 30,000 feet, you're down to 1 to 2 minutes. At 40,000 feet, you have 15 to 30 seconds. And at 43,000 feet, which is the certified ceiling for many modern jets, you have 9 to 12 seconds. If there's a rapid decompression where the cabin pressure drops suddenly, you can cut those numbers in half, which means you'd better hope those oxygen masks deploy fast. Cabin pressurization isn't just a comfort feature because it's the only thing keeping passengers and crew conscious. Aircraft maintain a cabin altitude usually around 8,000 feet for older aluminum jets, or about 6,000 feet for newer composite aircraft like the Boeing 787 and Airbus A350. And this takes serious engineering. The Concorde, flying at 60,000 feet, maintained a cabin altitude of about 6,000 feet, but it required a much heavier and smaller windowed pressure hull with a differential of 10.7 pounds per square inch to pull that off. The engineering ceiling hits hard when you look at what the fuselage can handle. An airliner is basically a pressurized tube that gets squeezed and released thousands of times over its lifetime, and the maximum pressure differential it can handle is limited by the materials, the thickness of the hull, and how many pressure cycles the structure can withstand before fatigue cracks appear. For most commercial aircraft, that's around 8.6 to 9.4 pounds per square inch, and you can't push much beyond that without serious consequences. When you're at 41,000 feet with an 8.35 psi differential, you're right at the limit of what the pressure hull can safely handle, while keeping the cabin at 8,000 feet, which is the regulatory maximum under FAA rules. Go higher and you either need a much heavier and stronger fuselage that cuts into your payload and range, or you accept a higher cabin altitude that makes passengers uncomfortable and potentially sick, and neither option makes commercial sense. Helios Airways Flight 522 in 2005 shows us the deadliest example of pressurization failure. Ground engineers left the pressurization selector in manual mode, and as the Boeing 737 climbed, the cabin never pressurized. The crew misinterpreted the warning sounds and didn't put on their oxygen masks, then were progressively incapacitated by hypoxia, while the aircraft continued on autopilot until it ran out of fuel and crashed. All 121 people on board died. Engines that can't breathe, wings operating in a razor-thin flight envelope, and a hull that's already at its structural limits paint a pretty clear picture. But here's the thing. Even if you could fly higher, you probably wouldn't want to. Most commercial jets cruise between 33,000 and 40,000 feet, because that's where the aerodynamics work best for their weight. Every aircraft at every weight has an optimum altitude where the lift-to-drag ratio is maximized and fuel burn is lowest, and as the plane burns fuel and gets lighter during a flight, this optimum altitude rises. That's why long-haul aircraft do step climbs in 2,000-foot increments, gradually working their way higher as they get lighter. A 2024 study of nearly 4,000 Turkish Airlines flights found that every additional 1,000 feet of cruise altitude reduced hourly fuel burn by 26 to 28 kilograms. Cruising 10% below optimum altitude increases fuel consumption by roughly 10% on a 747, which adds up fast when you're burning thousands of gallons per hour. The sweet spot for subsonic jets is that 33,000 to 40,000 foot band, and the math backs that up. This altitude range sits right in the middle of RVSM airspace, which stands for Reduced Vertical Separation Minima and runs from 29,000 to 41,000 feet. In this zone, air traffic control can stack aircraft with only 1,000 feet of vertical separation instead of 2,000 feet, which makes the airspace much more efficient and allows more planes to fly at their optimal altitudes. When RVSM was implemented globally between 1997 and 2005, airlines saw about 2.5% fuel savings per trip on studied routes just from being able to fly closer to their optimal altitudes, and that's real money. Above 41,000 feet, you're back to 2,000-foot separation, the air traffic gets sparser, and the efficiency gains disappear entirely. The Concorde flying at 60,000 feet seems to contradict all these constraints, but the answer is simple. It was willing to pay the price. Concorde had a small and incredibly strong pressure hull, tiny windows, powerful engines optimized for high altitude and supersonic speed, and it carried far fewer passengers than a 747. The aircraft was also phenomenally expensive to operate and never turned a profit during its entire service life. The physics didn't change, Concorde just accepted trade-offs that no commercial airline operating subsonic flights would ever accept. The U-2 spy plane operates above 70,000 feet, and the SR-71 Blackbird had a service ceiling of 85,000 feet, but these are specialized military aircraft where cost and passenger comfort don't matter. The pilots wear pressure suits because the cabin can't be pressurized enough at those altitudes to keep them conscious. and that's not exactly compatible with commercial service. Modern commercial aviation operates in a narrow altitude band, not because engineers couldn't design planes that fly higher, but because going higher doesn't make economic sense. You'd need heavier airframes, less efficient engines, more complex pressurization systems, and you'd lose access to the most efficient air traffic corridors, all to cruise in an altitude where the flight envelope is dangerously narrow and emergency descents become nearly impossible. The 41,000 to 43,100 foot ceiling you see on modern airliners isn't arbitrary or random. Physics, human biology, structural engineering, and economics all point to the same conclusion. This is as high as subsonic passenger aviation can practically go. Unless someone invents a fundamentally different way to fly, which is exactly what NASA and companies like Boom Supersonic are trying to do with new supersonic designs, that ceiling isn't going anywhere. The next time you're on a flight at 38,000 feet, remember this: you're not flying low. You're flying at the edge of what's physically, biologically, and economically possible for a tube full of people moving at 500 miles per hour, and that's exactly where you want to be.